In this lesson, in the series of lessons that are coming up, we are going to be looking at electricity. In particular, we're going to be looking at conductors and insulators, and what is a conductor and what is an insulator. To start off with, I've got the definitions up on the board for you, not dictionary definitions, but just a very simple understanding of what these two things are. Sorry about the reflection. A conductor, simply put, allows electricity to flow through it, while an insulator is the exact opposite. It stops electricity from flowing through it. Now, if you think back to our lessons on lightning and in weather, dangerous weather, we spoke about lightning being a specific type of electricity. I'll give you a moment to try and remember what kind of electricity that is. Starts with an S, T. Static. Static electricity comes from the word stationary, which means not moving. If you remember how that electricity works, it was the particles of dust and water droplets in the atmosphere that rub against each other and create a positive charge. And that charge builds and builds, and it's just stored in the cloud until it's able to connect with the ground. If you remember the negative charge that the ground has, that sends up the streamers towards the cloud is able to make a connection, and all of the stored energy in the cloud is able to dump itself into the earth all at once. But there is that electrical charge that is stationary. We are looking at the type of electricity now that flows. Okay? This electricity is what we call a current, because it flows. It moves in a circuit, and it always wants to flow in a specific direction. Now, it's important to bear in mind that electricity is dangerous. Okay? If you don't know what you're doing, it's very, very dangerous. Something as simple as a cell phone charger can kill you. There's enough current in that cell phone charger to stop your heart. Okay, so don't go and experiment with electricity. Don't go and open electrical devices that you are unsure of. Always ask somebody to help you if you've got a problem with an electrical device, because electricity can kill. That said, we are going to experiment with very, very small amounts of electricity in class. The currents that we're dealing with here are very small, and they are harmless. Nothing will happen to you if you had to be copying the experiments that we're going to do in class. I just want to point out this. Just appears like magic, eh? The flow of electrons is electricity. If I can explain it to you in this way, just imagine this. You have got, remember I used this before in our static electricity lessons. Imagine you've got a huge dam or reservoir full of water. Okay? That is what we call potential energy. It is energy that is just sitting there waiting to do something, waiting to be unleashed. Okay? And then you have got your hose pipe connected to that source of energy, and you've taken that hose pipe towards your garden and you want to water your vegetables. Okay, now that is a massive source of energy or a massive source of water for a very small application. Or you can just have a little tank, 100-liter tank of water with your hose pipe connected to that going towards your garden where you need to use the water. The hose pipe is what we are going to be referring to as a conductor. It is taking the water from the source to the destination that it is being used at. It's taking the water from the tank, and it is allowing it to be transmitted or transported to where you need it in the garden. Okay. Now, the greater the source, the greater the potential energy that the electricity has, the more force it's going to want to flow with. And that flow is what we call current. That is how many electrons are flowing and how fast they are trying to flow at a particular time. So if you've got a very small hose pipe connected to a huge tank, that water is going to squirt out the end of that hose pipe quite far because it's under a lot of pressure. You've got that huge tank of water pushing all of its weight through that hose pipe to the end of that hose pipe. There's going to be a lot of energy coming out of the end of that hose pipe. What you could do is, if you didn't want that long spurt at the end, you could have a smaller tank, lower the amount of energy with that same hose pipe, and it's going to have less force at the end. Or you can make that hose pipe bigger, which means there's not going to be as much force. The water's not trying to push its way through such a tiny opening to get to the other end. Of course, the bigger the pipe, the quicker the tank will drain. The smaller the pipe, the slower the tank will drain. With that in mind, I want you to just follow me onto this next topic of the flow of electricity, what makes a conductor, and what makes an insulator. So what I've got set up here is a very, very simple circuit. These are 2 batteries, okay? This is like our water tank, or our little dam that stores our energy. And here we've got a circuit. This could be our hose pipe that's taking our water all the way through to where it's needed in the garden. And when I join the hose pipe together, hopefully you can see that, the light lights up. What this is showing us is that there is a complete circuit. And the only reason why we use a light is because it's a very simple way to show that there is a current flowing through these wires. It shows us that electricity is moving. And the moment we disconnect it, it shows that there is a disconnection in the flow of electricity, and therefore no power is flowing. Does that mean that there is no longer any water here? Does that mean that there's no longer any energy here? No, there is still potential energy. It is just being stored. You need to turn on the tap, or in this case you need to make the connection in order to complete the circuit and in order for electricity to flow. Now, this is a simple way to use electricity. We know this, light. It creates light for us at night. We're able to see in the dark. But there's also another form of electricity being used, another form of energy being created here. That's not light. Anybody? Light is the simple. But if you had to hold this bulb, how do you think it would feel? It is hot. Electricity is being converted from one form. As it flows through here, it's being turned into another form of energy, from an electrical form of energy into heat and light. But before we can use electricity, it needs to be able to flow. It needs to be conducted. And it needs to be conducted through a material that allows those electrons to flow freely. It's pointless you having all of this energy here if your material that you're making the electricity flow through is not a good conductor. Think of it in this way. Imagine you have got your hose pipe connected to your tank that's going to your garden, and this hose pipe is full of holes, or it's got bits of mud or rocks stuck inside the hose pipe. Do you think that the water is going to flow freely? No, it won't. It's going to be blocked up. It might be leaking out into places that you don't want it to be leaking out, wasting your energy, wasting your water along the way. The concept is pretty much the same with electricity. If you've got breaks in your wires where the wire can touch against something else or touch the ground, you're going to be losing a certain amount of electricity along the way. Also, if your wires are not good conductors, the energy is not going to get to where it goes. So we're just going to have a very simple experiment this morning, and I'm going to show you different materials that make good conductors and others that make very poor conductors. How's that? Like magic. So I have got our favorite ruler made out of stainless steel. I have got a not so famous ruler made out of plastic. I have got a pencil which has got a graphite core, but it is surrounded by wood. I have got a pair of scissors which is stainless steel at the front, but it has got plastic and rubber for the handle. I have got a cell phone charger cable, and I have got a rubber band. And we're going to test each one of these on our circuit and see if we are able to get our light to still light up, which will indicate that we have got a complete circuit. So the first one being the most obvious, the ruler. What is our prediction? It's made out of stainless steel. Do we think that this is going to allow electrons to flow? is electricity going to flow? Is our circuit going to be complete? By putting this into our circuit, we are basically going to determine whether or not stainless steel is a conductor or an insulator. Does it allow electricity to flow through it, or is it going to stop electricity from flowing through it? And it's quite simple with our crocodile clips. We just clip one end on and touch the other end to it. Our light lights up. That basically means electricity is flowing through our ruler. But watch this, it's quite interesting. If I drag the crocodile clip along the ruler, you'll see the light starts to flash. And that's as the crocodile clip goes over the writing on the ruler, the paint. The paint itself is an insulator. It, for that microsecond, stops the electricity from flowing. If I had to put the crocodile clip next to 10, you see the light flows. And if I put it on the paint, no electricity flows. So that's quite interesting. Just the paint alone could stop the electricity from flowing. Let's look at another option here. We now have our pair of scissors. We're going to clip our, let's do that this way, clip our crocodile clip onto the stainless steel part. And our prediction, obviously, stainless steel, we've already determined that does conduct electricity, as you can see. However, when we come to the side that is now got plastic and rubber on it, there is no circuit. Electricity is not flowing, which means that the flow of electrons is being stopped. It's getting as far as the stainless steel, and then it is no longer being allowed to flow through the plastic. That is a simple way to show us that plastic is an insulator. Plastic stops electrons from flowing. Let's look at another option. We have here our rubber band. And what is your prediction? Is it going to flow or is it not? It's quite simple. It will not. Rubber is an excellent insulator. We spoke about this with our, see the circuit is still on. We spoke about this with our safety measures in a lightning storm. Wearing rubber shoes has saved people's lives from lightning strikes. Rubber is an excellent insulator. What about our plastic ruler? We've already determined that the plastic on the pair of scissors was a good insulator. And same again, circuit is still on. There is no electricity flow through plastic. It is an excellent insulator also. Interesting one here. The pencil. Would you say that this is a good conductor or a good insulator? Now, it depends on where you touch. Circuit is on. The wood is an excellent insulator. Wood is an excellent insulator. It does not allow electricity to flow through it, especially when it is dry. However, I'd like to point this out to you. The graphite within the pencil does allow some electricity to flow through it, but in this case, not enough to light up our light. Now, the reason why I say this is interesting is because this graphite has probably been mixed with other types of materials. Graphite that is used in a fishing rod or in a golf club, you'll see that there's a sticker on the side of that graphite that says do not use this in a lightning storm or near electrical wires, because normally graphite is an excellent conductor of electricity. Now in this pencil, because of its hardness, it's been mixed with other compounds that do not allow electricity to flow. I'll try this again with a pencil that is made of more graphite and less of the other compounds, and we'll see if we can get this light to light up. So now I've got a pencil that is of a slightly higher quality. This is an HB pencil. The previous one was an H pencil. Now watch carefully the light. That's connected to the graphite in the pencil. I hope you can see that. Even though it's not as bright as it normally is, because it's a better quality graphite, it does allow some electricity to flow through it, but because it's so dim, it shows that there's a certain amount of resistance. There's some electricity that is not being allowed to flow through. But graphite can conduct electricity. That is the reason why, if you've got a graphite fishing rod or a graphite golf club or even a hockey stick, it is important not to get close to electrical circuits with that. Don't play outside in the lightning storm. You're carrying a very, very good electrical conductor. And lastly, we've got our cell phone charger cable, and as you will imagine, it's been designed to conduct electricity very well. So we shall try that now. There you go. I'm just holding the two ends together. And that is a very short, not too short, a very brief introduction to electricity and electrical circuits. I hope that this makes sense to you and that you've enjoyed this lesson. And we shall continue with this topic throughout the course of the next couple of weeks. I'd really love to be able to do more of this with you and for you to experiment with the circuits for yourself. But ask your parents at home if you do have options to make a safe circuit. You just need a couple of batteries that you can buy at the shop with a holder for them, or you can tape them together. And then you just need some cheap electrical cable, one to the negative, the other side to the positive of that battery, and a small light bulb or even an electric motor, and you can replicate this very simple experiment at home. Please remember, do not play with electrical circuits that have got high voltage or electrical circuits that you are unsure of. You will get hurt. Okay? Thank you very much. Have a nice day.